you should get one. I made extra copies because I figured people would say, I lost it or whatever. Even though I see people throwing them away, but that's life. All right. We read this thing, and on Friday, you're going to have a very similar situation where you're going to have an experiment. It's going to be on the computer, so make sure you bring the computer. So first, quiz, and I already gave you the checklist. Let's go down this. I'm going to post it. You have the checklist that tells you what's going to be on the quiz, so you know what's on the quiz. You know it's going to be scientific method, accuracy, and precision. And so I'm telling you right now, what you're going to have is an experiment just very similar to the data nugget. All right, and you're going to have to do the following, the stuff that we're about to do as we go over the answers to the data nugget. As soon as I go over all the answers, that is due in the box with your due date. I'll put that into Schoology today. So I'm going to want these answers on a separate sheet of paper. You keep the questions, but as I go over the answers, so you keep this, because you did it on this theoretically, right? You did it on what I handed out to you. You keep that, put a hole punch it, put the due date, today's date, which is the 22nd, I believe. Is that right? August 22nd. So you put today's date on it, on what you're turning in, and at the top of this, and this goes in the binder for August 22nd. So again, let me draw it out here. And I just want to be clear, because I don't want anybody telling me they didn't know, they didn't understand, when I literally have many examples of me even drawing it out. So on this side, you're going to have your data nugget. The answers that you originally had, you're going to correct them. And you're going to have something you're turning into me with all the answers on it. And then over here, you're going to have today, since this is Thursday, August 22nd, right before the quiz, you're going to have your green checklist that has a summary of everything that's going to happen before tomorrow, since tomorrow is the quiz. Now remember, tomorrow we only have 40 minutes because we have a shortened schedule due to the fact that we have a whole school assembly. The quiz is only 20 minutes long, so that gives you extra time if you need it. Literally, you can have up to double the time. And if the rest of the class is ready and you need more time, we can maybe find another place to take the quiz. So time is not going to be an issue for you. However, I want to emphasize to you that on state exams, on AP exams, on SATs, in the very soon to be future, in the very soon to be present for you, you will have to deal with time constraints. Meaning you're going to have a lot of your tests will end up being timed. All right. So the first as you read through this, has everybody read through this? Let me start with that. I know some people came in late, some people didn't get a copy, even though there were extra copies, didn't know where they were, weren't listening, whatever. This was done a week ago, correct? Yes? I just want to make sure you got this a week ago. Ladies over here, especially those of you that fall off chairs. Do we have, what? Do we, just remember, you came for me first. So when we read, everyone read this, is that correct? Yes. All right. Scientific question. The question, they gave you the question. So remember, how do we start the scientific method? We start with an observation. And the observation is the Arctic is melting. Ouch, that's a big deal. North Pole's melting. Santa Claus is in trouble. Then the next question, the question they asked based on this observation, I'm just breaking down the data nugget into the various parts that we've been talking about. Our observation was the Arctic is melting. Do you see how I'm using an abbreviation? I put OBS. I didn't have to write observation. Then it says a question. And well, first you do research. And they did the research for you. This is an observation. So somebody said, oh, let me go find out what's going on with the Arctic, blah, blah, blah. And they went to the library. They read some papers. And they found out that there were they wrote it in what's called, in this example, and on tomorrow's quiz, they gave you background. Background in a scientific paper is a summary of the research done by the person who did the experiment. So background is when we tell you you have to go do research. Somebody went to the library, and if you're doing research, it's going to be you. Somebody went to the library and looked it up, or somebody got, in the case of a PhD, their background is still looking things up, but they also ended up studying, 6-7 years, that particular topic. A climate scientist may have spent his or her whole life studying climate. That's their background. They know what they're talking about. But how did they get that background? They studied. They went to the library. They read papers. So in a scientific paper, the background is a summary of what's necessary to understand the question, to phrase the question in context. So then you come up, after you do observation, after you do some research, you can form a question. And honestly, when you get a PhD or you become an MD or you become a nurse, it's the question you ask that becomes the most important part of the scientific process. Have anybody here watched House? The show House. Holmes is a good one too, but House is a doctor show. It's an older show. You can watch it, I think, still on Netflix. But it really does drive home the point. The reason House is it's a fantasy. It's not real. That's not really how doctors act and behave and are. But to be a really great doctor, you have to ask the right question. To be a great scientist, you have to ask the right question. In order to ask the right question, you have to have that background, that research. And you have to obviously be, intuitive and intelligent and all that. Yeah, we're all intelligent in this room. The part that we're missing is background. I like how she just looks at her when I say we're all intelligent in this room. I'm just saying. And you missed it. You missed her. Had that joke. All right, so question. The question is based on these climate models. So based on what climate models? The research, the background, right? So based on these climate models, how will the projected decrease in Arctic sea ice affect climate. Around the world. That's the question they're going to ask. And what they're saying is, look, we went to the Arctic, we took a meter stick, we drilled a hole, and we measured the ice. And year after year, what we're seeing as we do this measurement is the levels of ice in the Arctic are going down. They're going in this direction. It's a negative inclination, there's a decrease year after year of how thick the ice gets. And we're worried that at some point, if this keeps going, and they're like, let's extend the line, if this keeps going, in the near future, there won't be ice up there. And so, because this would be a zero, right, on a graph. So if we look at zero, if we take this line, this is the data, I'm going to put in red the data points that we measured. We measured these data points over time. We drew a best fit line, and you saw the best fit line in your study guide. We drew a best fit line, and when we look at this line, if we extend it beyond, this is what we measured. This is the last point we measured. This is this year's depth. But if we extend it, if we say this is how the direction we're going, and we extend it just in a few years, we might get to zero. I mean, that makes sense, right? You've done graphing before. We're going to do graphing in this class. But you understand that if you just extend the line, if this is what we measured, we didn't measure this, right? This is what we're guessing is going to happen. It could go up, right? It could drop even more drastically. It could stay the same. We don't know. Like, what are the different options for this graph? If we think about it, we could have a graph that does, you know what? Let me use the technology I have available to me and just make a copy of it. Let me make several copies. So we're not sure what's going to happen. There are many different things that could happen. What are the possibilities? Who can tell me what might happen in the near future with this graph? Look at it. What's a possibility? Let me zoom in. If we look here, what is a possibility might happen with this graph? This is the last data point here. This is this year. This white line is the best fit line. What might happen in the future? What about next year? Let's say this is next year. What might happen? Another dot where? Lower? Higher? Even lower than we had here? The same? Come on, guys, think. I said there's several right answers. Give me one. And go lower. So one possibility is it could do this. It could, what's it doing? It could, okay, why is it doing that? All right. Is this dead? The pencil dead? No, it's not again. Okay, not going to work with me today. This app is really beginning to bug me. I don't know why it's doing this. All right, it's working. There you go. It could go lower, right? It could do that. Yes, because we could have next year could be zero. Wow, well, how'd that happen? I don't know. We don't know what this is. Let me do this future dot in blue. What is that possible? Yeah, sure, why not? It's possible. What's another possibility for this graph? Stay the same, so it could just flatten out, right? It could just stay that's the lowest it's going to get, because year after year after that, it could just do this, right? Okay. What's another possibility? You can go back up. That's right. And maybe the next year it doesn't go down. Maybe it goes up. And the year after that it goes up even further. It goes up even. It could do this, right? That's another possibility. It could just go straight up in the future. It's pretty much the only thing that can happen. Or it could just do what? What's the last thing? It could just keep going the same direction, right? Maybe it just gets lower, but doesn't go lower any faster. It just kind of keeps doing the same thing it's been doing. Which one do you think the scientists are going to bet on? If you were going to bet money, which one do you think you would bet on? The last one, right? Why would you bet on this one? All of these are possible, right? They're all possible. Why would you bet on this one? Go ahead. You know the answer. It's exact. You're right. You would bet on the last one. You'd bet if I had these labeled A. Let me do another color so we don't get anything confused. A, B, C, and D. If we were gonna bet, you and your friend are like, I'll bet you, I'll wash the dishes if you get this. You and your sister are sitting around the house, or you and your brother sitting around the house. I'll bet you to doing the dishes that I get this right, and I think it's D. Why would you bet on D? All right, let me start again. I'm going to now pay attention and listen and think. 100 years ago, this was the depth of the ice. I kept measuring. I measured for 100 years. I measured, and every year it keeps getting lower and lower at this, according to this white line. Now I'm asking this is today. This is my last measurement today. Now, what am I going to predict in the future? Am I going to predict it's going to flatten out? Am I going to predict it's going to drop? Am I going to predict it's going to go up? Or am I going to predict it's going to keep going the same direction? Why? Because it's been happening like that for 100 years. What's changed? I don't know. I don't think anything's changed. It's the same thing. Have we changed anything, right? It's like... I don't know, what's something that stays the same every day for you? What's a routine for you? Something happens every day for most of your life, this happened. Something happens every day. I mean, the sun comes up, but not at the same time every day, so that doesn't count. Like in my house, my mom would every day, we would wake up to coffee. The smell of coffee. My mom would have coffee brewing in the kitchen every morning, bacon cooking, literally bacon and eggs and coffee every morning for my father. And we would smell that smell of breakfast every morning. That's what woke us up. Every single day. What do I expect? When I was a kid? What did I expect would happen? Did I expect that one day that smell wouldn't be there? No, I expect it's going to be there because that's what's been happening my whole life, right? So if you have a bunch of data points that are going in one direction and you just have to guess, you have to make a hypothesis, you have to guess what's going to happen. You're going to guess according to the trend, correct? The trend in my mother's home was breakfast, the smell of breakfast every morning. The trend, this is called a trend line. You guys have a trend of making TikToks. What'd you all say? Give me the money or whatever, right? Or whatever. Give me my money, right? That's a trend line. So you have a trend. Every time you turn on your TikTok, here, give me my money, or you get somebody to say it. Well, this is the trend in sea ice, the white line. So if I'm going to make a bet, and I'm going to make, and a hypothesis is a prediction, a bet is a prediction, right? You're predicting something's going to happen, and you're putting washing the dishes on the line. Here, we're going to predict that the sea ice is going to continue to go away. Correct? All right. So it says, based on the climate models, How will the projected, by the way, I'm going to say, I think I've said this before, but I'll say it again. Projected also means to predict. It's a synonym for, it can be a synonym for predicting. So when you say, how would the projected decrease? It's very similar to saying, how would the predicted decrease? Why are we predicting? Because of what? Why are we predicting the sea ice is going to keep going down? Because of what? The trend line. The trend is, that's what we're used to. Yeah. Sure. Which were on the words or the graph? So you're welcome. You get the trend line is predicting what's going to happen based on what's always happened. In the fall, the leaves always fall. Is it possible that the leaves don't fall off the trees one fall? Yeah, I guess. But would you predict that? You wouldn't bet on that, would you?
No. I wouldn't.
I wouldn't either, because we have common sense. Or rather, since common sense is not common, let's just say we have good sense. All right? Is everybody okay with that? All right, so let's go on. Let's make a hypothesis now. They say, what's the hypothesis? Well, they say they expected that compared to the control, the treatment models with reduced sea ice would have more extreme weather. So they said, the hypothesis, they said, which is that they're betting that the sea ice is going down. It's going to keep going down. They're saying, well, if that does happen, if the sea ice keeps going down, if the treatment groups it's not really a good way of saying it. Let me think about how to rephrase an if-then statement. We're going to just write if. So if you wrote if, it's all right. You're not. If the sea ice keeps going down, then those with less ice would yield or have more extreme weather. And again, what do we mean by extreme? We're talking hurricanes, tornadoes, really hot, really dry, right? And what do we mean by the models? What are those? When I use the word those, what are we talking about? We're talking about the models. So we have model 1, the US model, and the UK model. And we're going to have a treatment group. And a treatment group is the ones with less sea ice. And we're saying we're going to put in less sea ice. What if we put the ones where we say we're going to put some numbers into these models? They're computer models, right? They're computer guesses using math. I'm going to put different values in. If I put a value of less sea ice, because what did we say? There's several options. We could have less sea ice. We could have the same sea ice. We could have even less than we're having, or we can have more sea ice. They're arguing that if we put less in there, then those are going to put out more extreme weather. They're going to say, the models are going to say, we are going to have more extreme weather. All right. So that's what's going to happen. If you put in, they're saying if I put in less sea ice, then the model's going to pump out, more extreme weather. That's what they're going to say. And their argument is the 10th percentile reflects the temperature. You probably don't know what percentile means. You might have covered it in middle school. Percentile means how many, what percentage of, in this case, temperature. If you're in the 90th percentile, that means that you scored better than 90% of the people that took that test. So if you're in the 10th percentile here, the temperatures where 10% of the temperatures values are the 10th percentile reflects a temperature value where 10% of the values are below. So only 10% are below it. So it's a pretty low temperature below the value. Because only a few observations were colder than the 10th percentile, only 1 in 10 days, we define it as cold day. See, they're defining cold days and they're defining warm days. And they're saying anything that's colder than, anything that's at the bottom 10%, we're going to call cold. Anything in the upper 90%, we're going to call hot. So if we did a graph of hot and cold, what we would say is like, if this is temperature, and this is and these are days, and we plotted temperature in days, then we would say these are the cold days, the bottom 10%, and the top 10% is going to be the warm days or hot days. Everything else is in the middle. So this is it. This is the 90th percentile. 90th percentile, and this is the bottom 10th percentile. So these are remember I told you that cold and hot, maybe we were making jokes that just because you say it's cold doesn't mean it's cold. You have to have some reference point. Remember we talked about quantitative versus qualitative, correct? Cold is qualitative. Cold is data that's not, if I say it's cold, is that a number? No, it's just an opinion, right? So how do we make that opinion a number? Well, we can measure the temperature and say, look, if it's at the bottom group of temperatures, if the temperature falls here at the bottom end, we're going to call those cold. And if they fall up here in the top 90th, we're going to call them warm. So now I've taken that qualitative data and I've given it some numbers. That lets us do some calculations. Is that fair? Are we okay with that? Okay. So it goes on and they talk about 10 percentile. And then they look at the historic data and they put it all in a graph. This is the graph that confused everybody. So let's take a look. So these are different models. They use the different models in different places. Obviously, you're going to have to. Climate's going to be different in the desert than it is in the mountains, than it is in Europe versus Canada, right? You wouldn't expect the climate to be the same in East Asia as you would in Canada, would you? No. So what do you see at the bottom of this figure? That's right. And what does that mean? Why do they have those cold days, warm days? What does that mean? Why do they have those symbols? And what do we call that when we have a graph or a figure? Say that? A legend. Excellent. That's your legend. So cold days, again, those bottom 10 percentile, they're going to have a little thermometer, and they have and they fill in the, oh, for Pete's sakes, you guys are ridiculous. You're ridiculous.
How are we ridiculous?
I heard your little giggling.
I can't giggle and crackle. I can't.
You can. I didn't say anything about it except it's ridiculous. I can't do this right without. So let's just say this. Let's put a snowflake, and the other symbol that's there. They do a much better job, and that's gonna be your cold days. And then the warm days, they're gonna have that same symbol with the thermometer higher up. In fact, I'm not even gonna do the bulb. I'm just gonna do the rod, and I'm gonna say the cold days are down here, right? And over here, the warm days are all the way up, right? So we have cold and warm. And then wet days are represented by what? Raindrops?
Yeah.
All right. So wet days are going to be raindrops. And then dry days, they're gonna represent it by having this kind of wilted plant. And that makes sense, right? Because what do plants do when they get dry? They wilt. And we'll talk about why that happens later. So those are three symbols that they're giving. They're only looking at three different aspects of climate. How wet it is, how dry it is, how warm it is, or how cold it is. That's it. So according to the models, in Alaska, it's going to be, in Canada, it's going to be much warmer in northern Alaska. It's going to be colder in southern Alaska. It's going to be wetter in Canada. Do you see that? In western Canada. You see it in Greenland, it's going to be warmer in upper Greenland. It's going to be colder in southern Greenland. And it's going to be wetter in East Canada. You see how the models are saying? That's what they're saying. So we're predicting that these are going to be extremes. So when they say wetter, they mean floods. When they say drier, they mean droughts. When they say warmer, they're talking 100, 110 degree weather. It would be 102, 104 degree weather here in Cleveland. But in Alaska, it might be, whatever warm is for Alaska. And so that's how you read that graph, that figure. Do you see that? Do you see how you read it? So those are the results. They put it in the form of a figure. Those are your results from the experiment. So then they ask you some questions. Let's go to the questions. What is the independent variable in this experiment? Now that I've described the experiment as completely as I could, what's the independent variable? What am I changing, and what's the dependent variable? What's changing because I changed it? See, this is going to be on the quiz tomorrow, dependent, independent variable, right? They took a look at the data and compared the results of the controlled treatment groups, looking for different differences between the two. So what was the independent variable and what was the dependent variable? What changed because something else changed? What did they change? When they put it into the model, they put a value into the model. What is it that they changed? What changed because they changed the value? Well, let's go back and look at this. What was the hypothesis? If the ice keeps decreasing, then those days with less ice would be more extreme. And what value did they put into the model? What is the value they put into the model? Somebody said it. Less what? Sea ice. That's right. So the independent value is sea ice level. So you got it. So they said, well, if I put less in there, then I get more extreme. So what is the dependent variable? That's right. how many extreme weather events? Right? So the dependent variable is how many extreme weather events. The independent variable is the sea ice level. So what would you say? What was the control group, by the way? Can somebody find me the control group in the reading? Current sea ice levels, correct. So your control group is the control group was the current sea ice levels. And if those are the current sea ice levels and we change that level of ice, that's us changing that value that's going into the model. So then the independent variable is the sea ice level, and the dependent is how many extreme events. Okay. And then here they tell you all these different extreme events are going to happen. It looks like the central U.S. is going to have drought and low temperatures. On the East Coast, in the central U.S., you're going to have high temperatures. Low temperatures and a lot of precipitation. In the West, you have more precipitation and lower temperatures. So you're going to have a lot of different. So how many cold days were there? Look at it. Count. How many cold days? All around the world. Because this is the question. The hypothesis was all around the world. So we're counting all the extreme cold events. How many do the models predict around the world? How many? 7. According to you, I haven't counted them, so I'm going to go by what you said. So you counted 7 temperatures with a down arrow, correct? With a little snowflake. So 7 of them. So you would put in cold days 7 extreme weather events all around the world. How many in warm days? How many warm days? How many 90th percentile, which means extreme heat, are we going to have around the world? 4. So 4 warm days. How many wet days? 7. And how many dry days? 6. All right. So now, so these are 7 more days than the control. How many warm days? Again, you counted them already. 6 more than the control. What about the wet? 7 more than the control. And dry days? 6 more than the control. So now answer the hypothesis. Answer the question. What was the question? Going back to our notes. Notice these are notes. Based on the climate models, how will the projected decrease in Arctic sea ice affect the climate around the world? What would you say? The hypothesis is if the sea ice keeps decreasing, those with less sea ice would have more extreme weather. Do we have more extreme weather or not? Yes, we do. If with less sea ice, we have more extreme weather. How do you know? You counted them. You wrote it down. Correct? Now, can you handle writing because we only got a minute or so left. Can you handle writing the rest of these answers down? What evidence was used to write your claim? The evidence that we recorded off the figure, right? Explain your reasoning on why the evidence in the model supports your claim. Connect the data back to, well, you would say, we have 7 more. I'm going to make these up because I don't remember what you wrote down. 7 more cold days and 6 more dry days, whatever, right? Yes? Than the control. More than the control. Did the data support James's hypothesis? Use the evidence to explain. Since there were more, with less sea ice, there was more extreme weather. Yes, the data did support the hypothesis, correct? Yeah. Okay. What else could you do? What could James do in the future? How would you build on these questions? How much more? Could we do something about it? Could we change it? Could we add, is there a way to add sea ice? What if, there's a lot of other questions. What is increasing the temperature? What's melting the ice? So these are questions you can be asking. So I think I gave you all the answers. Whatever you wrote down today, put it there. Keep your questions. Review. Make sure you know your scientific method for tomorrow. You'll have a 20-minute quiz and plenty of time to do it in.